series, that's what we've been doing. And we are specifically talking about power series of a function. The grand idea would be, I tell you any function, and you figure out what the power series is. Now, we are kind of a long ways from that at this point, but we have talked about basically one example, and that is this. This is the power series for 1 over 1 minus x. And written with the summation sign, it looks like this. This one, you start at n equals 0, just so that you get that 1 right at the beginning. All right? So this is the power series for, this is kind of like a geometric, well, it is a geometric series over here with the r equals x and the a equals 1. And so when you add it up, you get, it's a over 1 minus r, which is, in this example, 1 over 1 minus x. And this converges when absolute value x less than 1. So you could say, if you want to say, in other words, the radius of convergence is 1. That's what we talked about last time. The radius of convergence is 1. And if you like, you could say the interval of convergence is the interval minus 1 to 1. So that's an open interval. All right? And this, you should just kind of memorize this basic thing. I mean, it's not so hard to remember. But this is the simplest power series of a function. All right? Now, how do we get power series of different functions? We started at the very end last time talking about this. You can do simple tricks to get variations on this basic function here. For example, you can do 1 over 1 minus 3x. And the simple trick is just, well, this is what you get when you put 3x instead of x up here. So this is the sum, n equals 0 to infinity. Instead of x, I'm putting 3x, right? And then that can sort of simplify as a series to 3 to the n, x to the n. Because when you write a power series, you want to see x to the n with certain coefficients. So this is kind of a preferable format for writing that. All right. Now, we did an example just like this last time, I think with a 2 instead of a 3. But something that we didn't say last time about this is, you can also say, what is the radius or interval of convergence in this case, by the same kind of plugging in trick. So the way that we got this was plug in 3x, up here, right? That's how we came up with the power series. But to get the radius or interval of convergence, we can also plug in 3x to that thing, right? It converges when absolute value x is less than 1. That's the standard version. This version will converge when absolute value 3x less than 1. So this converges when absolute value 3x less than 1. And in other words, i.e., absolute value x less than 1/3, right? The 3 in this situation, the 3 can just pull out of the absolute value sign, and then you can divide it onto the other side. All right, so that means, in this case, the radius of convergence is 1/3, and so the interval is minus 1/3 to 1/3. All right, the interval of convergence is always just the, these are power series centered at 0, so whatever the radius is, it's minus r to r, whatever the radius is. All right, so you can not only find the series for these things by doing this kind of simple tricks, you can also find the radius of convergence and interval of convergence. All right. Let's talk about some variations on these simple tricks, or how about something like this? Here's another example. Find the series and radius of convergence. all right? You have to decide what you're going to plug into that thing over there, all right? And there's a slightly different simple trick. Remember, the one that we know, sort of the memorized one, it looks like this, right? Anyone have a great idea for how we could sort of use this formula here to do this one? What's weird is there's a 2 there. If there was a 2 in front of the x, I would just plug in 2x over here. But there's a 2 over here. You might say, well, I'll just do this one, but I plug in, 2 instead of 1. That doesn't make any sense. So 1 is 1. You can't plug in something for 1. Any big ideas? I got a trick here. There's a special trick. I mean, this is also a simple trick, and that is I'm going to factor out a 1/2 like that. These certainly are the same, right? So if you ever see a different number where you want to see a 1 there, you want to see a 1 because that's how it needs to be a 1 in order for you to plug in over here. If you see something that's not a 1, you can divide that constant out and turn it into this, and now I can plug this over here using x over 2 instead of x. That's the trick. All right, so now we plug that in, and I get 1/2 times the sum, n equals 0 to infinity. And then instead of x to the n, I'm plugging in x over 2. So it now says x over 2 to the n. And as usual, I want to write this as some coefficient times x to the n. So this would be 1/2 the sum 1/2 to the n times x to the n. Or you could write 1 over 2 to the n if you like, or I suppose you could write 2 to the minus n if you want to get real fancy. All right, this is the series. And then what's the radius of convergence? Now for this, you have to, don't get yourself confused. This original trick that I did where I pulled the 2 out really doesn't have anything to do with anything. The radius of convergence is determined by what you see in the box. I should have written it there. It's this right here. So it's determined, no matter what other tricks I do, it's determined only by what I'm plugging in for x. And in this case, I plugged in x over 2. So to find the radius of convergence, I say x over 2, absolute value x over 2 less than 1. Because that's the part that I ended up plugging in for x, was x over 2. And then this, as usual, you solve for x by multiplying the constant over. It says x less than 2, so the radius of convergence is 2. All right. Simple tricks, really, but they can get you pretty far. All right. I have a couple more, and then I want you all to try some. I got 2 more, all right? One more, 2 more examples demonstrating one more simple trick. How about x over 3 minus x, all right? I'll keep this thing in the box. This really, every one of these questions is based on this thing that, I said you should just memorize it, although you do enough of these examples, I think you'll remember it naturally. X over 3 minus x. So when I see this 3 here, that's similar to the one we just did. I'm going to divide out a 3 from the denominator to turn it into a 1. That messes the x up, but that's fine because we can handle that by plugging something weird in for x. So I'm going to pull a 3 out of the denominator. And this says 1 minus x over 3, right? What can we do in the numerator? It says x. This is also a problem. I mean, it's not such a big deal, but we need to somehow deal with that. And we want it to say 1, but instead it says x. Any ideas? Yeah?
You can take out like a 1 over x?
Yes. From the denominator, you mean?
Well,
Take out a 1 over x.
like I was just like kind of using the same logic as the other thing where it's like you take out like a 3, so then if you do a 1 over x, x over 1, or x times 1 over x equals 1.
Yes.
I don't know if I'm making
I think
sense.
what you mean is just that.
Yeah.
I think what you were saying was
overcomplicating my
yeah,
work, but that's what I meant.
you divide by 1 over x, which is the same as just saying I factor out the x. All right? Yeah, this is almost sort of too stupid to count as a trick. I mean, it's not much of a trick at all, but if you want to see 1 here, you just put the x out front. So this right here is going to give me a series, which then we can just multiply through everything by x over 3 if you really want to. All right? So this was yet another simple trick. The 3 comes out on the bottom as usual, and then we can also just take an extra x out of the top. So what we get is x over 3 times the series, where I'm using the standard formula in the box there, but using x over 3 instead of x. So it'll say x over 3 to the n. All right? And that's basically it, although I'm going to kind of simplify a little bit just to make it look like a power series. That is to say, I want it to just say the sum of something times x to the something. So this will say x over 3 sum, I'll write it as 1/3 to the n, x to the n. And actually, usually when you see this kind of a thing written out, they don't like to have coefficients out here. When I say I want a power series, I should say n equals 0 just. When I say I want a power series, I mean I want the whole answer to just be the sum of something or other. So this, the entire answer I want to write as sum. And how we do that is just like stick this thing back inside the sum, right? We have talked about already that when you have a series, you can pull a constant out of a series, or you can sort of distribute a constant into a series. Now this, you may not think of that as a constant because it has an x in it, but for the sake of the summation, which is over n, we do consider the x to be a constant. The variable, if you like, here is n. That's the summing variable. But the x will be the same every time. So my final answer will look something like x over 3. This is not my final answer. I'm going to do one more thing with that. Right? And then, again, just to combine terms on the inside, I believe what this says is 1 over 3 to the n plus 1, because there used to be n of them, and now I just got one more. And then the x's is now going to say x to the n plus 1. Because there used to be n of them, but then there's one other. All right. It's all simple tricks. And what about the radius of convergence? Again, the simple trick that we did here doesn't affect anything. The radius of convergence is determined by what got plugged in over here, and that is x over 3. And so instead of this being the radius of convergence, it's, can I write ROC for the radius of convergence? It is x over 3 being less than 1. And that is to say absolute value x less than 3. So the radius of convergence is 3. All right. All right, one more. Same old simple tricks. This one looks a little bit more interesting just because of the way it works out. How about x over 1 minus 2x squared? All right, this time we don't have to do anything to get a 1 in the bottom, so I like that. And we can just factor out sort of the single x into the front and then say this is 1 over 1 minus 2x squared. And then we do the usual thing, the standard formula, 1 over 1 minus x. So I'm going to plug in to that. There's x out front, and then the series, n equals 0 to infinity, of, I'm plugging in 2x squared to the n, like that. This one is a little strange, I suppose. We can handle it. All right, this is basically the answer, but just to simplify a little bit. How do you simplify the nth power here? X sum, what do you say? 2 to the n, yeah, 2 to the n, x to the 2n, right. An nth power like that, you do nth power on each of those two things, and the one, when you do it on the second one, x squared to the n, you multiply exponents, so it's x to the 2n. Great, and then just to put everything inside the summation just so that it looks like a pure power series. It'll say 2 to the n x to the 2n plus 1. All right? This is my series. This is kind of cute. You know, if you want to, you can write this again, not using the sigma, right? Like, what do the terms here look like? They look like odd powers of x with powers of 2 in front of them. So this means, I think it's kind of cute that this works at all, but it means 1 times x to the 1 plus 2x cubed plus 4x to the 5. These are odd powers of x with the powers of 2 as coefficients. The next one would be 8x to the 7. Very strange, but it is true. All right, and what about the convergence? The convergence converges when, you know, the standard form is absolute value x less than 1, but here what I did was I plugged in 2x squared. So this will say absolute value 2x squared less than 1, which means I divide the 2 across, absolute value x squared less than a half, and then you can take a square root here, like so. So this is a little strange, but the radius of convergence here is 1 over root 2, or the square root of a half, if you prefer. All right. It can get a little weird at the end. Any questions about that one? I got a few for you to try. It's all the same kind of simple tricks, and then we'll talk about some more interesting things. How about, so each time, find the series and find the radius of convergence. How about 3 over 2 plus x, x squared over 1 minus 3x, and 2 over 1 plus x squared. See what you think. I'll come around and see how you're doing. Find the series and the radius of convergence. Because this will be an alternating sign. When you write it that way, it's negative 1/3, which is negative. This 3 is a straight factor time, and then you take 2 and a half.
Okay, gotcha. Gotcha.
Okay? Yeah. That makes sense. Don't forget about the negative. Negative 3. Yeah. Okay? This is a rough now plug in. Are you in some kind of calculus class now?
Not exactly.
Yeah. This is like towards the end of the basic calculus class. Okay. Yeah. Doing all right?
I'm just gonna look to answer it.
So that's the series.
Oh, it is.
No. Yeah, and the n plus ones came about. Yeah, it's because there's extra x outside. I was not happy. Well, you probably should do that. Yeah, which you did also. But there's no x to the back.
So you just gotta put it in. You don't have to do it.
Yeah, you don't have to do that. Well, yeah, I suppose if you'd like, you could say 3 over 2 to n plus 1. I mean, that's what this is.
Excuse me.
Yeah.
You just let me know how many times
Yeah, this is great.
up to here.
Sure, I mean, I actually.
Wait,
I know, I'm just not.
I know there's actually steps.
This is a plus.
Oh, so.
Yeah, so that's just this.
No,
That's-
it's art, it doesn't just turn into a thing, but.
And then you have to add this back.
What you're plugging in here
Isn't it?
is actually.
But then, I don't understand.
Doing all right?
Where do you go?
I think it's when you put this part in, then it's here, and then like this is x to the 1.
It just moves into the.
So then if you wanna have it say like in this thing, so then the x is out.
Okay, see how you have this plus?
Oh, I see, okay, so he splits
Right,
this
that
into
actually.
x, like 1/3 times x times this much.
This has to be.
And then he adds
When you go to plug
and he
in.
adds it here. So the original thing is x over 3 to the n.
This now is a plus.
But then we can split it into.
It says plus here, but I'm looking at it as one.
But you have to bring back the other x.
Yeah, then you bring back the other x. So it's x to the 1 times x to the n. Then it's x to the n plus.
It's kind of.
And then it's like there's 1/3 times 1/3.
Yeah.
But there should be more stuff that says sum of one over, like this one over thing with that.
Okay, so,
Should not, I mean, this is not.
okay.
It's very straight. Maybe you're gonna
I know that it's supposed to be negative because
Oh my goodness.
Yes.
Just here?
Yes, yeah. So this is. Well, if we use 2 back 1/2.
My astronomy class doesn't.
The effect is the sun is.
It's my science.
It doesn't change this.
No, that's just.
All right? Yes. So this gives up the plus, you know, the thing we keep on plugging into. So the idea is, think of this as one.
Like that's
like rather than this, so I should say
3x to the n.
And then
Sum of x
This is almost perfect.
Yeah, like this. Yeah. Yeah. I don't think like we do
No.
like
The only thing I need here is that's a
Oh, wait, is it? Yeah.
but like the standard version of format is minus. So
Take a
so the effect of that
this
is
is my x. And
That
then I
is
just
that.
so that's
That's
my
my
r,
r,
yeah.
yeah.
Plus
So then
that's 1 minus negative
3x
x.
to the n.
I have it. You have to put it back in.
You don't just like r doesn't have to already.
Can we talk about these? Oh, you got-
Sorry. I just,
give me a moment.
would you combine these to have it just negative over two of them?
So it's
Try to
just
simplify them.
when you're like just saying
Okay.
r,
Oh,
it's
okay.
just whatever is
So
to
it's
the end.
3x.
Oh, okay, but like we don't have to do that. We can just keep
Absolute
it.
value.
That would-
And then
Okay.
divide by 3.
I would put it,
the series.
Yeah.
Put it first.
yeah, because I like to see constant and then power of x. All right, let's try. Maybe the first one was a little tricky because of the plus in the denominator. We did one last time with a plus in the denominator. I hope you remembered. Anyway, this one, you factor a 3 out from the numerator because I want the numerator to be a 1. And then you also should pull a 2 out of the denominator, which makes the denominator 1 over x, 1 plus x over 2. And then this becomes, I got my 3 halves out front, and then it's going to be the sum n equals 0 of negative x over 2 to the end. This is a little tricky, but as I was going, it seemed like most people figured it out. This plus, I want it to be a minus in the standard formula. I think of this instead as 1 minus negative x over 2, which is why negative x over 2 goes inside when I plug it in. A little strange, but this is basically my answer, although I like to rewrite it so that it's always some numbers times some power of x. And in this case, it should look like, I'll bring the 3 halves inside also. 3 halves times negative a half to the n times x to the n. This, if you really want, you could combine as something like 3 times minus 1 to the n over 2 to the n plus 1. If you really, I would not, necessarily want you to write it this way, but if you really want to combine everything as much as possible, it would look like that. Make sure you don't lose the minus 1 to the n here. So this is actually an alternating series with some other weird coefficients in it. All right, that was the series. What about the radius of convergence? I would say the thing that we plugged in was negative x over 2. So for the radius of convergence, I look at this and then sort of solve for absolute value x here. The minus sign ends up not mattering because of the absolute values, and I multiply the 2 across. It says absolute value x less than 2. So that's the radius of convergence is 2. I hope that's what you got, something like that. This was probably harder than the other two. Maybe I should have reconsidered the ordering of them. All right. Any questions about that one? All right. The second one there was x squared over 1 minus 3x. So this one is a little more straightforward. You just take the x squared out for now, and then do this series for 1 over 1 minus 3x. It should be the series of 3x to the n, right? And so this is putting the x squareds back in. It says 3 to the n and then x to the n plus 2 is how I would write this. Because when I do 3x, the whole thing to the n, that's the same as 3 to the n times x to the n. And then I have 2 extra x's out here, so when they come in, it becomes x to the n plus 2. I hope that's what you said. And then the radius of convergence, you go absolute value 3x is less than 1, which means the radius of convergence is 1/3. Everybody seems satisfied with that. I hope so. And then the last one there also had a plus in the denominator, but otherwise it was not so weird. So this one I would take 2 out, 1 over 1 plus x squared. And so when I plug in, I get the sum and then minus x squared to the n. 1 plus x squared I think of as 1 minus x squared, which means the thing I plugged in was minus x squared. And then just simplifying, oops. It looks like minus 1 to the n times 2 times x to the 2n. This is how I would write it. Make sure you appropriately put the parentheses around minus 1. This is actually different from just writing that. When you write this, just because of the order of operations, this means 1 to the n, which is always 1, and then negative. This will actually be negative every time for each n, whereas this is alternating the way it ought to be. All right, and then the radius of convergence here, you say x squared in absolute value, well, minus x squared less than 1, which means, x squared is less than 1. Take the square root. X is less than 1. So the radius of convergence is 1 here. It seemed like people were coming together all right. The people got to come together. That's what I always say. Any questions or thoughts about that? Once you know what you're doing, I mean, it's basically simple tricks that you're plugging together. All right. What about some more sophisticated tricks? I have basically one non-simple trick, and that is what we call, one last trick, term by term differentiation and integration. Term by term differentiation. This is using the fact, the simple tricks so far have just been like plug in 2 instead of 2x instead of x, right? You can do that for anything, but to get a little fancier, you can think of these things as functions which are differentiable as if they were polynomials, and you are allowed to take the derivative of both things. So what I mean by that, I'm going to write this as a theorem because actually this is not obviously legal because it involves weird operations with an infinite sum. I don't want to talk about the proof of this, but it is a true fact that I'm going to write this formally, that you'll see what I mean and why it's called term by term differentiation. If I have one power series that I know about, let's say looks like the sum Cn x to the n, so that means just some coefficient in front of x to the n. If this is a power series and f of x is differentiable, that means the derivative exists, then the power series for f prime of x you can get it by term differentiation. That means you can look at this thing and just straight up take the derivative of each term in the series. So the power series for f prime of x is f prime of x equals the sum, and on the right side I'm going to take the derivative. It says x, well, the constant Cn just stays like it is because it's a constant. And then it says x, I take the derivative, it becomes n x to the n minus 1. All right? And this is referred to as term by term differentiation because we took the derivative of each term in the series. Term by term differentiation. All right? This is another simple trick. I mean, it's considerably less simple, but another trick you can do to find the power series for certain functions. And you can also do this with integration. So this was the term by term differentiation. So I will continue the theorem. And the series for the antiderivative the series for antiderivative f of x dx is also given by term differentiation. So the antiderivative, we can also just take antiderivatives inside the sum. Now I'm not going from here. I'm going from here, the original series. I'm going to take the antiderivative each time. So the constant, again, the constant will stay like it is. And then this x to the n turns into 1 over n plus 1 x to the n plus 1. So this is Cn times 1 over n plus 1 x to the n plus 1. And then, unfortunately, just because we always do, we have to add a plus c because we just took a bunch of antiderivatives. You're actually doing the antiderivative infinitely many times, like for each term of the series. All right, this is the term by term differentiation. I might as well put this in a box also. Term by term differentiation and integration. And one last thing about this, which is sort of good news. You might wonder, because I did something so weird to both sides of this, what about the interval of convergence? It turns out, by some magic, the interval of convergence is the same. So the interval and radius, whatever you want to say, I'll say interval, since that's more specific. The interval of convergence of f and f prime and also the integral f are all the same. So when you do one of these more sophisticated tricks, taking derivatives or whatever, you don't have to do anything weird to the interval of convergence. All right. That is kind of a hardcore theorem that I don't really want to talk about why this is legal. But anyway, let's just see how we can use this. We can use this to come up with interesting new examples. So for example, let's just look at our favorite, simple example here. What about this? Etc., right? Maybe I'll write it as a series. The series x to the n. All right. Let's take the derivative on both sides then. So this is a series for one function. I'm going to do the derivative on both sides. First of all, the left side. Now, in order to do the derivative on the left side, I'm going to think of it as 1 minus x to the negative 1 power. And so the derivative of that, using the chain rule, is minus 1. So the derivative of that is minus 1 minus x to the negative 2 times negative 1. That negative 1 at the end is from the chain rule, the derivative of the inside. So it all ends up being 1 minus x to the minus 2 power, also known as 1 over 1 minus x squared, like that. That's the left side, right? So that is the left side. And what's the right side? The right side is you just do the derivative each time over here. So the series, can anybody say what's the derivative x to the n? This is not a trick question. Yeah?
N times x to the n. N times x to the n minus 1.
Yeah, right. N times x to the n minus 1. And this is a true power series fact. And this converges because the derivative has the same interval of convergence, this one also converges for absolute value x being less than 1. All right? This is the series for 1 over 1 minus x squared. And if you wanted 1 over 1 minus x cubed, you could take the derivative of this again, and you would get a series for 1 over 1 minus x cubed, and so on, right? You could take, if you want 1 over 1 minus x to some power, you take that many derivatives of the series. All right? If I were to write these out in terms, what it looks like, this would say, this is, the n equals 0 term is 0. The n equal 1 term says 1x to the 1x to the 0, and then 2x to the 1, 3x to the 2, 4x to the 3, etc. That's what this series looks like if you want to see the terms one by one. All right. So this is a new power series that we have. Let's try and get a little fancier. How about... This is still, in my opinion, in the category of just like some random function. There's nothing, like this is not all that useful of a function. You know, it's not like one of my favorite functions or anything like that. But here's one that really is a well-known and useful function. How about, what about 1 over 1 plus x? All right, now the series for this we already know by, you know, the simple tricks already. We have determined it's that, right? Which is the sum n equals 0 to infinity minus 1 to the n, x to the n. This is the series for 1 over 1 plus x. Now you could, if you want to, you could take the derivative throughout here, which is all fine and good, but I want to see actually what happens if you do the integral of this. So let's integrate term by term. What happens? On the left side, it's going to say 1 over, integral 1 over 1 plus x. This is not so hard of an integral to do. Anybody got a suggestion? How about a u substitution? I like that idea. What do you want for the u?
1 plus x.
Yeah, let's say u equals 1 plus x. That means the du is just dx, right? 1 dx. This is a nice old-fashioned u substitution. I don't know if you have been feeling, if you don't like this material lately. Can't we just do u substitutions again? I don't know. I kind of like what we've been doing better than u substitutions. But what's it going to be? It's just 1 over u, and then the dx is just equal to du, right? And so what's the integral of that? Yeah? Yeah, it is ln of, to be technical about it, absolute value of u plus c. And this, of course, is plugging it in. ln of absolute value 1 plus x. All right? So that's the integral of the left-hand side. What that means is actually what we're going to end up with is a power series for the natural log, which is actually quite useful and a very different looking function than the ones that we've been talking about so far. So anyway, that's the left side. The right side is this, and you do the integral term by term. So this is the left side. The right side is the sum. I'm going to do integrals term by term. Minus 1 to the n, x to the n, dx, right? Sorry, I scrolled it off. We did the integral of the left side and got this natural log. Now this, whatever that is, should equal the integral of the right side. That's going to be this integral. This is like ultimate Hollywood mathematics. Integral inside of a sum. Can you believe it? That's crazy. A foolish beginner calculus student says you probably shouldn't do that because the integral is a kind of a sum. Are you doing like an integral inside of a Riemann sum? No. I'm doing term by term integration. They love this in the club. You will turn the heads. Do the integral of that. All right, this is an integral dx. So this minus 1 to the n is a constant as far as the integral is concerned. We just have to do the integral of x to the n, which makes it 1 over n plus 1 x to the n plus 1. So this is still a sum, but the integration gives me 1 over n plus 1 x to the n plus 1, like so. All right, so what's my conclusion then? So the natural log of absolute value 1 plus x is, unfortunately, we have to put a plus c, which I'll write at the front just so it's not confusing. The series 1 over n plus 1. Sorry, I forgot my minus 1 to the n. That needs to be part of this. You integrate just the x to the n, but this is a constant, so it stays in here. I'm going to put it in the numerator there, like that. Minus 1 to the n. So this is an alternating series. X to the n plus 1 plus some constant. All right. This actually, on the right side, is a very kind of a nice looking series. If you write the terms out, it says the natural log 1 plus x is some constant plus n equals 0 over here. these are n plus 1, so it's really like x to the 1, and it's minus 1 to the 0, which is positive. So it's this. And then it's alternating. And you get very nice sort of simple pattern here, right? It's always 1 over something times x to the something. And the signs alternate. This is a cute formula for the natural log. Now, this one thing that's very kind of disappointing is the c. Can we figure out what the c is? C is a number, right? And ordinarily, you just leave the plus c in your answer, and you have no way of determining it. But actually, in a term-by-term integration, you can actually solve for the c because we have two sides of an equation here. We can solve for c by plugging a particular value of x. By plugging in, anyone have a value that you would like? I mean, you can plug in whatever value you want. It should be one which is convenient to actually do the calculating without using a calculator, for instance. What do you like for plugging in x? What's your favorite number to plug into weird formulas? I would say there are two choices, this or this, right? Those are my favorite numbers to do. When it comes into plugging, I'm thinking about what is going to be convenient to plug in on the right-hand side. I would say probably 0 is going to be better. My go-to would be 0s and 1s. I don't really want to plug in 1 over here to get an infinite sum, but if I plug in 0, those all are 0. So I'm going to plug in x equals 0. You could make it work with x equal 1, but I don't really like it. Anyway, what that gives me then, on the left side, it'll say natural log of 1 plus 0, right, which is 1. And on the right side, it'll just say c plus a bunch of zeros. And anybody remember what is natural log of 1? It is 0. So c is 0. So this, you can tell your moms on your break. This is a true formula about the natural log. It has this very sort of pleasing, simple pattern over here. What is I find this very interesting, and I hope you can sort of put yourself in the mindset of the old school folks who first discovered how to do this. The natural log, before this point in history, before this formula was discovered, which is basically the whole idea of power series, more or less immediately gets you here by doing some simple tricks. Before this was known, basically if you ask somebody, what is the natural log? They'll be like, that's just some weird function. Nowadays, if someone asks you what the natural log is, if you don't know anything about this person, probably the best thing to say is it's just some weird function. You got to push the button on your calculator. Like, if you really want to get into it, I could tell you more than that, but that's the surface level. And it was even worse in the old days because they didn't have calculators. It was like, it's some weird function and we don't really even know what the values are. Or you have to work really hard to find the values. But it turns out somebody, like after the fact, after the natural log function was invented by somebody else, some other guy discovered that actually this totally weird function has this very natural, simple looking formula for it, which nobody, like the guy who invented the natural log, didn't know about this and didn't expect it. This to me is a sort of a deep and profound fact about the nature of mathematics and the universe, is that mathematics is created by one group of people with a certain intention in mind, but actually it turns out there are things that are true that they never intended to be true. It's a weird thing about the way that there are sort of hidden realities beneath what we think of these functions. So eventually we are going to get to similar formulas for, say, sine of x, cosine of x, e to the x. It turns out they all have sort of secret formulas that nobody knew about until the theory of power series was developed. And this led to huge advances, including this is actually not a bad way to calculate the natural log. If you don't have a calculator and I asked you to tell me, like, what is the natural log of 7, this is not a bad way to do it. You could plug in 7 here, and I mean, it would be a pain, but you could imagine just by hand calculating, say, the first 10 terms of this, and it'll be pretty close to the actual value of the natural log of 7. All right, I think I'll leave it at that. So we will not meet at all next week, but we will the week after. I'm going to post a homework assignment, but it won't be due for a whole week and a half.